In this video, we will discuss how to train the multilayer neural network. To be more specific, we will discuss the backpropagation algorithm. Stochastic gradient descent was used to train one neuron. Here, we want to train our neural network as a whole computational system. So, in the network we have many layers, and in each layer we have many neurons. They are connected with each other if we talk about the subsequent layers. So here, let me draw some simple neural network. And we see that here we have the connections between the neurons of this layer and between the neurons of this layer. So if this is the output layer, then next there will be the last function. Using this function, we can get the error because our network predicted some values, some probabilities of our classes, and we have the true labels, and we will propagate these errors going backward our neural network. So the main idea behind the backward pass and behind the backpropagation algorithm is the chain rule. Because using the chain rule, we can obtain the errors for this neuron using the errors of this neuron. So we use the information of the output layer of our network, and we use this information to update the parameters of the neurons that are in the layers that are in the previous layers in that network. So the chain rule helps us to apply some formal algorithm which name is backpropagation to update the parameters of the network for it to make fewer mistakes. So to update it in the right way. Let's dive into the details of backpropagation algorithm. Let me draw the schematic representation of the last hidden layer in the neural network and the output layer of the neural network. Keep in mind that there are the connections between the neurons of the last hidden layer and the output layer. Here is the outputs for the last function. We will consider the neuron of this layer, this neuron. Let the weights of this neuron be wij vector. And from the previous layer we have the outputs O1, O2, OM. And the weight matrix of this layer is equal to M by LR. Here M is the number of neurons in the previous hidden layer. Last hidden. LR neurons, Lout neurons. And here we have the wij. So something here, wij, it is the wj is the weight vector of the neuron number j in this layer, and the I is the index of the weight in this number vector, numeric vector. So it's the number, just the number. And now let's formulate the transformation made by this neuron. So phi j, which is the activation function of this layer, and this neuron, each of these neurons, applied to the sum of w j multiplied by O k, where k is from 1 to m, plus bj, where This is the bias of the J neuron. And it is equal to OJ. And let's draw it here. Here is the connections of this neuron to the next neurons. Here's OJ and here's OJ. Let's denote this by net J. So OJ equals phi J applied to net J. We can use the gradient descent for this weight to optimize it. So let's write Wij equals to Wij minus alpha multiplied by the delta Wij, where this term is just the partial derivative of our loss with respect to Wij, and we can write Wij minus alpha then Wij. Let's denote the loss by E. It's just for the simplicity. And now we want to uncover this term. The loss function depends on the OJ, and OJ depends on net J through the phi J, so through the activation function of this layer. And here we have phi J, we have net J and OJ. Loss depends on the OJ, and net J depends on Wij. Keeping this in mind, we can write the following expression. So multiplied by OJ with respect to net J, and this is multiplied by net J with respect to the Ij. Oh, sorry, here it is not in the right place. Let me draw it correctly. Here we have OI, so O2, the second input, the input number I, and the input number M. And this is the J neuron. This is the J neuron, and Wij is just the weight number I in the weight vector of the J neuron. Let's continue to uncover the terms of this expression, and we will start with the partial derivative of net J with respect to Wij. We can write it. We have net J has this form, and we can write it just in the same form. Wkj multiplied by O cap k plus bj derivative with respect to Wij. We know that the addends in this sum that don't depend on Wij will be equal to 0. So here we have just Wij multiplied by OI cap plus bj doesn't depend on the Wij2, and here we have just OI cap. So we have uncovered this term. Now let's uncover this term. Let's just write this, and now we have that OJ is equal to phi j applied to net j, and we can write phi j applied to net j with respect to net j, the derivative with respect to net j. And here, if phi j, for example, if it is the sigmoid function, we have the formula for its derivative with respect to its argument, and here it would be phi j applied to net j multiplied by 1 minus phi j applied to net j. And this is the expression for this term. Let's uncover the last term in this expression. There are two cases when we talk about this term. The first case is when we talk about the output layer. Here we have the partial derivative of E with respect to OJ, and it equals to the loss applied to Y predicted Y and the true labels with respect to OJ. And if it is the output layer, the OJ just equals to the Y pred J. So it's the prediction of the gth neuron of the output layer. We have this network. We'll talk about this network, and now let our loss be the squared loss. And we can derive this. We can write Y minus Y predicted squared with respect to Y predicted gth, and it is equal to 2 multiplied by this multiplier is usually omitted because we can just multiply the hour loss by 1/2, and this wouldn't lead to any problems while during the optimization of our network. So we want to minimize our loss, and there is no difference between minimizing our loss or the half of our loss. So we have this expression in case of the output layer. In the second case, we talk about the neurons which are not the neurons of the output layer. For example, when we talk about the neurons of the last hidden layer. Let's write the partial derivative of the error with respect to OJ, and here let's talk about this neuron, number J, and this output neurons, number U and V. We can note that the error depends on the output of the output layer's neurons. We can just write it here. The output of the neuron U and the output of the neuron V with respect to the OJ. And now let me just denote it with some mark. And now we can continue to uncover this, keeping in mind that all the neurons in the output layer are not connected with each other. And we will get OL, net L, LJ. Here we have just the same situation as before, and this term will be equal to WJL and this is the partial derivative of error with respect to the output of the output layer, and the partial derivative of the outputs of the output layer with respect to the net L. It's just the linear transformation of the output neurons. So here we have the recursive form of the formula that we had before, that we have here. These parts of the expressions are just the same. Let's briefly summarize what we have done so far. We have uncovered the partial derivative of the error with respect to the weight ij, number ij, and we have got this expression, and then we uncovered each term independently. And we come up to the final expression for the partial derivative of the error with respect to the outputs of the Gauss neuron. And now we can write it in the following way. Take some time to realize the expressions displayed on the screen. It's very important to understand what we have reached so far. One of the most important things in backpropagation is that it allows us to calculate the updates for the layer using the outputs and its outputs and inputs during the forward pass, and using the weights and deltas in the layer next to this layer. So in backpropagation, we firstly, during the backward pass, we firstly calculate the updates for the days of the output layer. Then we can, using them, as you can see here, we can calculate the parameter updates for the previous layer through this expression, using the outputs of this layer and the parameters of the output layer. And this allows us to effectively update the gradients, to effectively apply gradients in our network and update the parameters of the multi-layer neural network. And this completes the backpropagation algorithm. So, the summary of the backpropagation algorithm. The backprop allows us to compute the gradients in network effectively. It allows us to train the network as the whole computational system. For each neuron, we can apply the gradients to its weights and update it in an effective way, using the inputs and outputs of each neuron during the forward pass. So we can just store the inputs and outputs of this neuron, of each concrete neuron during the forward pass, and then use it in the backward pass, in backpropagation.